we're in the middle of Bessel's equation, right? Solving one kind of Bessel equation. So we were solving x squared y double prime plus xy prime plus x squared y equals 0. Right, this was one of the Bessel equations, and we had found one solution. What have we done? Let's remember everything. We had gotten that we ended up with this a naught r squared x to the r plus a1 r plus 1 squared x to the r plus 1 plus summation n plus r squared a sub n plus a sub n minus 2 x to the n plus r at equal to 0, right? Right. This is what we've gotten, and we had used that to. We saw that the roots were double root. R could be 0 or 0, and we calculated one solution using that recurrence relation, right? We got one solution was y1x is a naught times 1 plus summation -1 to the m over 2 to the 2m n factorial squared plus to the 2m from m equals 1. And that's where we finished up. And we were just about to find the second solution. So, so remember, that the second we know what the second solution looks like, right? We worked it out. The second solution is going to be y1 times the natural log of x plus x to the r1. Well, r1 is 0, so we don't really need that. X to the 0, I'll just leave it in this one. X to the r1, a sub n prime r1, x to the n, right? And from 1 to infinity. And that's fine. We worked this out two classes ago, or maybe last class, maybe one class ago. Okay. And so our right, and so what we need to do is we need then to determine the derivatives of the a sub n. Right, these things depended on r, and we need to figure out what they are. I said that this was going to be dislikable and a pain, and so, but we'll do it. And we won't do much of it, and I will not ask you to do much of it. But let's just see how it works. And it involves some nice tricks. Okay, so let's look at the even terms first. Let's look at the even terms first. Okay, and let's recall that we know that a sub 2m of r is going to be negative a sub 2m minus 2 of r over r plus 2m squared. Right, that's from our recurrence relation. Yeah, Christy.
How did we know that we are in the case that the ANs are functions of R rather than just constant coefficients?
Because we're in the case of the repeated roots,
Okay.
right? We're in the repeated roots case, and you remember how we solved it, right? The trick was to think of the R as a variable.
Oh, and then
Right.
okay.
And then differentiate with respect to that.
And that's
variable.
how we got that.
That's how we got that.
Okay.
Right. So basically, once we see the repeated roots, we know that's the trick we're going to play. We're going to let the R vary and differentiate, and let the R vary, and in that case, these guys become functions of R. The coefficients become functions of R, and so we can differentiate them. Also.
Why did you replace n with 2m?
Just to indicate that it's an even number.
Oh, okay.
Yeah. So, right. 2m and m is like 0, 1, 2, 3. So we're dealing with even terms, right? And for the odd terms, I'll say 2m plus 1. Okay. So what do we do? 2m from the recurrence relation. Does everyone see that? Right? We want this thing to be 0. Right? We want this thing to be 0, and so we get that recurrence relation. Right? And then, as usual, you sort of, you go down, you step down m steps, right? And at the bottom, you get that this is going to be -1 to the m times a naught, right? Over r plus 2m squared, r plus 2m minus 2 squared, and then subtract by 2 all the way down till you get r plus 4 squared and r plus 2 squared. Right. You step m steps down to the bottom. Right. So if we're going to differentiate this, so all we need to do then is take the derivative of this, right?
I have a question.
Yes.
In your denominator there, why do you adding at some point and then multiplying for the points?
Oh, this should be multiplied.
Okay.
Thank you. You say this. Yeah, it's because I'm crazy. I've made so many errors in the last 2 days. The other day I said, so in my calculus class, I said, so -4 minus 4, and that's 0. And the whole class was like, and they were silent. And I was like, what's wrong? and after about 1 or 2 minutes, one of them, said, isn't that -8? They were so shy. Yeah, but I've made so many errors in the last 2 days. I said I'd give up on arithmetic. So please watch me carefully. My daughter has just started a pre-kindergarten program that starts at 8 o'clock in the morning. So I get up at 6:45 now, when I usually get up at 7:30 or something like that. So I think I'm a bit off. I didn't think I'm reading my sorry. I'm not even looking. Yeah, it's true. You barely registered to me. Yeah. Okay, so I'm sorry. I'll leave it off today from. Okay, so what do we need to do? We need to differentiate this, and what's a good way to differentiate something like this? Something with a lot of products. Don't say the product rule. Do you guys know? Do you guys know the good trick for differentiating? What?
Does it have to do with logarithmic?
Yes, exactly. Logarithmic differentiation. Right. So, for example, so let's say f of x, let f of x be that huge product without the constant. So r 2 equals 2. Okay. And so the trick is, of course, to take the log of both sides, right? So you take the natural log of both sides, right? The log is good because the log turns this sort of thing this sort of thing into a sum, right? Right? You get the log of r plus 2m to minus 2. Right? The log turns the product into a sum. That's what's useful. Right, and of course, you can pull those minus 2's out. Minus 2's out. The exponent comes out and becomes a product. Okay. So we just use the two useful properties of the log. Right? The log of the product. The log of the product is the sum of the logs, and the log of something to the power is the power times the log. Goes to the log of the log. Okay, and then you differentiate, right? So differentiate both sides. Do dx of that is do dx of that. Right? And then on the left-hand side, we're going to get f prime x over f of x. Right? And the right-hand side, we get negative 2, 1 over r plus 2m plus 1 over r plus 2m minus 2 plus 1 over r plus 4 plus 1 over r plus 6. And so, f prime is f of x, right? F of x was that product? Oops. 1 over r plus 2m squared plus 2m minus 2 squared plus r plus 4 squared r plus 2 squared. Right? You get f of x. This is our f of x, and then times this thing, minus 2 here, and then 1 over r plus 2m plus, all the way down to 1 over r plus 4 plus 1 over r plus 2. Just as Eskimos have different kinds of varieties of snow, professors have different kinds of chalk. And so I can only write with one kind of chalk. And actually, that's probably, I don't think that's true, but it's not true that Eskimos have a variety of words for snow. Or like more words than we do. Anyway, read it.
Is that long-term addition or multiplication?
Thank you. It's multiplication.
Did you keep the
Are there any errors?
exponent?
What?
Did you keep the exponent? Okay.
Yes, that's okay, right?
Oh, so,
Right, we have the negative 2 from this guy. We have f prime. F prime is this thing, that's negative 2 blah, times f of x, right? And this guy is the f of x. So that's okay.
It's kind of like Newton's method.
What?
Sorry, go ahead. It's like Newton's method when you like look for roots of when you're using like MATLAB or something.
No, it's quite different. Yeah, it's not the same. Newton's method is this sort of iterative thing of taking tangent lines and trying to use the tangent lines to find the roots. Right, so you go here, right, and then you take a tangent line here, and then you see where see where it crosses and then keep the tangent on point, and then you sort of go back and forth, you get narrowing of the grid. That's something different.
What is, I'm sorry, I think I'm just missing a portion, the first part of the derivative there, like 2 times that whole thing.
Yeah.
It's just not used.
So let me read it again. No, I'm not going to read it again. I'll make it narrow. But we just, is everyone okay from, you differentiate this and we get this? Everyone okay with that? Right? And then we're looking for f prime, right? We want the derivative, so multiply both sides by f of x. Right? So f of x then, I'm sorry, f prime then is this thing
Oh, okay.
times f of x. Right? F of x is this. Okay, so I just moved f of x from here to here. I just multiplied both sides by f of x. And that is the method of logarithmic differentiation, right? That gives us the f prime. Right?
Quick question, why do we have just the r, why made it r plus 2? Is it something to do with,
It's just the number of steps that we went down, right? We go down m steps, so like 1 step down to. Do we go down m steps? Are you right? Should we go down to r itself? I don't think so. I think this is right way.
okay, I just didn't know. And that's just because we go down to only m minus 1, or like, when m equals 1.
Yeah, we go down. So let me think.
So is m not 0? It's just 1 to infinity?
Yeah, because if m equals 0, we just, then we say that like a naught is equal to a of negative 2.
I guess what's this? What's the second? So we're going to stop when m is 1, right?
And that's r plus 2, okay.
We're going to stop when m is 1 because then we'll get that this guy. No, this is right.
Right.
This is right. We stop at m.
But then does m go from 1 up, or does it go from 0?
I mean, this formula is valid for.
Yeah, if we're just going to be super picky, m equals,
Oh,
zero,
yes,
right, yeah.
yes.
I think that's what she was saying.
Okay, yes.
I
No, no. Yeah, because there is no a sub minus 2.
Right.
Yeah. Okay. Okay. So what do we get? We get that so what do we get? We get that a 2 and prime of r then is this thing -1 to the m a naught over r plus 2m squared down to r plus 2 squared times -2 times this thing 1 over r plus 2 plus 1 over r plus 2m. Right. So we're just writing it up. And you notice that that this part here, is actually a sub 2m r, right? Comparing what we just erased. Right. This thing is this thing here. Okay, so this is that formula. A sub 2 of time of r is this. And what did we need? We needed a sub 2m prime at 0, right? Well, that's a 2m at 0 times minus 2 times 1 over 2 plus 1 over 4 plus 1 over 2m. Right? Which is, we worked this out last time, right? A sub 2m of 0. This was negative 1 to the m a naught over 2 to the 2m times m factorial squared. And here, we'll change this minus 2 to a minus 1 and multiply everything by 2 in here. And we get 1 over 1 plus 1 over 2 plus up to 1 over n. Which is the beginning of the harmonic series. Okay. And the book denotes this by h sub m, sum of the first m terms in the harmonic series, which you've seen before when you first studied convergence of series, convergence and divergence of series. Yes?
Are all of the, is essentially for all the problems that we do, we're not always going to end up with the same sum, right?
No, no.
So, like the end result will be different for
Yes.
every problem.
Yes. Yes, yeah, and so, I mean, this one worked out in a very pretty manner, or is working out in a very pretty manner. It may not work out so prettily.
So is the difficulty because the harmonic series diverges? Is that what the difficulty is going to be?
Well, no, actually, that won't be any trouble because look at what's happening. We are dividing by a huge term, right? This thing, this growth, if you think about the harmonic series, it's a slow growing series, right? But we're dividing by 2 to the 2m, right?
So is the part where you said it's like more difficult, is this the difficult part we just worked out, or is that still to come?
This is the difficult part.
Okay.
Yeah, so the difficult part is just the, I guess it's not difficult. It wasn't that difficult. It was just that we needed to find explicitly what a sub 2mr was.
So this is pretty much the end answer, is what you're saying?
Yeah, we're almost done. Okay, we're almost done. So at least we know that, right, we knew that y2x was like this, y1x x plus x naught, x to the 0, excuse me, a n prime 0 x to the n. And we know what the even terms look like. Right? The even terms look like this: n from 1 to infinity, negative 1 to the n plus 1, h sub m over 2 to the 2n, and factorial squared x to the 2n. And the only thing left to do is this actually is the end. This actually is the end, because what happens is that the odd terms turn out to be 0. Okay, the odd coefficients turn out to be 0. So in fact, the odd coefficients turn out to be 0. So
Do we know that because of this?
we don't know it yet. We don't know it. Well, I'll show it next. So I skipped over it to do the nice even terms first, because it's prettier.
But sometimes will they not turn out to be 0?
Right.
In which case you would just add it on.
Yeah, yeah. So like, here we've only got the even terms.
But then would you have like a separate equation for y2 for odd terms, or would it just be added on?
No, it would be, you'd have this, you'd have y1x, l1x plus the whole series. Okay, the whole series, and the series would have both even and odd terms. Okay. Or I guess if you figure them out separately, then you have one guy for the even terms and one guy for the odd terms. Okay. But for us, it will turn out that the odd terms are all zero. The odd coefficients are all zero. Everyone all right? Okay. Okay. So the argument showing that the odd terms are all zero is a little bit ugly. So I'm almost tempted to skip it, but I think we should do it. The odd terms, the odd coefficients are zero. And here's how they show it. They say, well, look, A1 R plus 1 squared is 0. Right? This came out of from the identity theorem. Right? The x to the R plus 1 term. This is the coefficient of the x to the R plus 1 term. And so they say, well, let's differentiate this thing. Differentiate it with respect to R. Right? And you get 2A1R, R plus 1, plus A1 prime R, R plus 1 squared is equal to 0. And so, in particular, 2A10, if you evaluate at R equals 0, you get that 2A10 plus A1 times 0 is 0. And we saw yesterday that A1 at 0 was 0. And so this implies, so A1 times 0 has to be 0.
Where did we see that?
We did it yesterday. Remember when you took this thing when you took R to be 0, you got A1 equals 0.
Oh.
Yeah. Or we saw what we can see clearly. A1 at 0 is 0. So A1 prime is 0. Okay. Now let's use the recurrence relation again. A and R, we remember, is this thing. Negative A sub n minus 2 of R over n plus R squared. If you differentiate that, you get negative R plus n squared, A sub n minus 2 prime of R, plus A sub n minus 2 of R times 2 R plus n over n plus R to the fourth. You get, you get that A n prime of R equals that. Okay. And again, evaluating at 0, you get A n prime of 0 must equal to negative 1 over n squared A sub n minus 2 prime of 0 plus 2 over n cubed A sub n minus 2 of 0. Okay. So, and then you basically use this formula to bootstrap your way up, as you might expect. Right? You say, well, look, A3 prime then is some combination of A1 prime and A1 at 0. But both of those guys are 0. Right? Both of those guys are 0, so you get A3 prime is 0. Right? both of those guys are 0, right? None of the people are not. Right? A3 prime of 0 is going to be some multiple of, right? It's going to be right, some multiple of A1 prime of 0 plus some other multiple of A1 of 0. But we just said that both of those guys are 0. Right? Both A1 prime and A1 are of 0 or 0. So we get a combination of zeros. We get 0.
How did you get that A1 prime to 0?
Right from here, we know that 2A1 plus A1 prime is 0, and A1 is 0.
Okay.
Right? So 2 of 0 plus this thing is 0, so it must be 0. It's not exciting.
Will that always happen if or if for A1 or for like A2 it equals 0? Or I mean for A0? So let's say this situation happened for the even numbers, could that still occur?
Could they all be zeros?
Yeah, could all the evens be zeros and all the odds be numbers?
Oh, could the opposite occur?
Yeah.
Yeah, sure. Yeah, so this is all just peculiar to this one case. And it you know, but it will work out in some other way. It will, work out in some other way. So what you see here then is that A3 prime of 0 is 0. But again, we saw yesterday that all the odd terms for r equals 0, all the odd terms were 0, right? So we saw yesterday, last time, that a sub 2n plus 1 of 0 is 0 for all n, right? For n equals 1, 0, 1, 2, 3, etc. Right? All the odd terms, when we use the 0 root, turn out to be 0. Okay. And so we get A3 prime of 0 is 0, and A3 of 0 is 0, right? And you see that then we get A5 of prime, right? So these two together, just like the A1 prime and A1 being 0 gave us the A3 prime, right? The A3 prime and A3 give us the A5 prime, right? A5 prime is 0. And again, from yesterday, we know that A5 itself was 0. And then these two give us the A7, etc., etc., etc. And so you just keep on bootstrapping. You do an induction, right? By induction, you get that all of these odd guys are 0. Okay, right? And so that's why, that's why we don't need to worry about the odd terms, the odd powers here, right? Only the even powers are going to persist. So this is the end. This is the second solution to the first the Bessel equation of order 0. So that's the fundamental set of solutions for the Bessel equation. Let me make sort of a cultural comment. Traditionally, one takes the second solution